Hi, my name is Yassini Lavla, and this is my Lab 3, Magnetic Fields of a Bar Magnet for Physics 2212. Okay, so first I'll start off with the purpose of this lab. The purpose of this lab was to look at magnetic dipoles. For example, a bar magnet represented a magnetic dipole. Another purpose of this lab was to use the Biot-Savart law, which talks about the relationship between the magnetic field and its magnetic dipole moment. Also to explore off-axis and on-axis, to explore magnetic fields off-axis and on-axis at different distances, gain a visual understanding of magnetic fields, observe the relationship between distance and magnitude of a magnetic field. Next, some concepts and equations that we needed. Like I stated earlier, we did have to use the Biot-Savart law in this lab. We also had to use, for the second equation underneath that, was the magnetic field on the magnetic dipole on axis equation. We also had to use some distance dependent equations to graph our data. And going back to that Biot-Savart law before I move on, we also used that to compare the distance-dependent measurements in this lab. Okay, over here are my calculations or the numbers or my raw data from this experiment. As you can see at the bottom, toward the very bottom of the screen, you'll see the magnetic field at the location 45 degrees off axis from the dipole, and my graph, which graphs ln b of x versus ln of r. Some further calculations or analysis, just to continue on from the next slide. After doing my experiment, putting in all my raw data into the Excel sheet, my n was 2.163. My ln of k was negative 13.03. To calculate the dipole moment, I did k is equal to e to the negative 13.03. To solve for the dipole moment, which gave me 4.13 Tesla. Okay, before I go on to the computational model or further on in the stock report, I just wanted to talk about something that I observed while doing this lab. One thing I observed was as the magnetometer moved closer, i.e. the distance decreased, but as the magnetometer moved closer to the magnet, the x component of the magnetic field did increase. And also when the magnetometer is far away from the magnet, in other words, like the distance increases, it measures a near zero magnetic field in the x direction. Also, the Earth's magnetic field must be subtracted from the measured y value to get a value for the Earth's field. Alright, so next I'll talk about my computational model. At the top half here, that's just the beginning of the code where I basically just completed that function they gave to us, which allowed us to calculate what a magnetic field would be due to a dipole at a certain location. The bottom half here is where we wrote out the 2 axes and 4 perpendicular locations that represented our observation. Basically, our observation locations for our on-axis and perpendicular locations. Okay, next is the second part of the computational model. So first, the second part was to basically have Python represent 2 arrows that represented the magnetic fields for on-axis. And here we basically created 4 arrows to represent the magnetic field perpendicular to the axis. Okay, finally, the last part of the code, which basically allowed us to calculate the magnetic field, to calculate the magnitude of the magnetic field at an observation location 45 degrees off axis. Here is my final model here, my final photo, and also all the values that I got. The what if questions. For the first one, I said the magnetometer measurements would have been different and inaccurate since it would also be considering the Earth magnetic field along with the bar magnet. And for the second one, I said the magnetic field direction would be the same and would almost be doubled. Also, the value of the magnetic field would be more than the value we obtained from our current setup. Thanks for watching, and I hope you have a great day.